Hey there, and welcome. So just take a look around you for a second. You're probably sitting on a solid chair, maybe you've got a glass of liquid water right there, and you are for sure breathing in a gas, the air. We're literally surrounded by these three states of matter all day, every day. But have you ever really stopped and thought about what truly makes them different? Okay, let's dive right in. On the surface, it seems pretty obvious, right? A rock is clearly not the same as water, and water isn't the same as steam. But here's the thing. The real answer isn't in what we can see with our own eyes. Nope. It's hidden away in this secret, invisible world. So, in this explainer, we're going to pull back that curtain and find out what's really going on. So, here's our game plan. First, we'll start with what we can actually see. Then, we'll take a trip into that secret world of particles. After that, we'll get into the story of the three states, figure out how they change, and finally, we'll look at the actual data that proves the whole thing. All right, first up, let's start with what we all already know. This section is all about the simple, everyday stuff we can just, well, observe. Okay, so picture an ice cube. It's a solid, right? It's got its own shape, its own volume. You can't really compress it or squash it down. Now, what happens when that ice melts? You get water, a liquid. It doesn't have its own shape anymore. It just takes the shape of whatever glass it's in. But the volume is still fixed. And finally, if you boil that water, you get steam, a gas. This stuff has no fixed shape and no fixed volume. It just expands out to fill the entire room. So these are the basic rules we can all see. But why? And that is the big question. So let's get to the answer. This is where we get to that big aha moment. It turns out the reason solids, liquids, and gases act so differently is because, underneath it all, they're all being powered by a hidden engine, this incredible world of tiny, constantly moving particles. And this whole incredible idea, it has a name. It's called the kinetic particle theory. And honestly, at its heart, it's pretty simple. It just says that everything, your desk, that drink you have, the very air you're breathing, is made of tiny particles. And that keyword kinetic, well, that's just a fancy word for motion. Because these particles, they are never, ever still. You can really break this whole theory down into four main ideas. Okay, number one, everything is made of particles. Got it? Number two, they're always moving. Always. Number three, the big difference between a solid, a liquid, and a gas isn't the particles themselves, but how they're arranged and how they're moving. And finally, and this one is super important, when you add heat, you're just giving those particles more energy, which makes them move around even more. Okay, so now we have the theory. Let's put it to work. We're about to see how this secret world of particles perfectly explains the world that we actually see and live in every single day. And this table here, it's a really great way to see it all side by side. Just look at the columns. You can compare how the particles are arranged, the forces between them, and how they're actually moving. So let's just go through them one by one. Okay, first up, solids. In a solid, the particles are packed together in this super neat, orderly pattern. It's called a lattice. And the forces holding them together, they're incredibly strong. That's exactly why a solid has a fixed shape. The particles can't just wander off. They're basically locked in place, just vibrating, right there on the spot. All right, now for liquids. The particles are still really close together, but look, their arrangement is all random and jumbled up. The forces holding them together are weaker now, and that's the key. It allows the particles to break free from their fixed spots and just kind of slide past each other. This is a perfect explanation for why a liquid can flow and take the shape of whatever you pour it into. And finally, we get to gases. And here, it's just total chaos. The particles are super far apart, and there are practically zero forces holding them together. This means they're totally free to just zoom around rapidly and randomly in every direction, bouncing off each other, bouncing off the walls of the container, you name it. And that's exactly why a gas will always, always expand to fill whatever space you put it in. Okay, so we've got a good handle on the states themselves now. But what about when things change? When a solid turns into a liquid or a liquid turns into a gas? Well, this is where that fourth rule we talked about comes into play, turning up the heat. So let's walk through the process of melting step by step. You take a solid, like that ice cube again, and you start heating it. You're basically just pumping energy straight into its particles. They start to vibrate, and then they vibrate more and more violently, Eventually, they're shaking so much that they actually become strong enough to break the forces that were locking them into that neat little lattice. They just break free. And there you have it. The solid has melted into a liquid. Boiling is pretty much the next level up. You just keep adding heat to that liquid. Now the particles aren't just sliding around, they're moving faster and faster, colliding with each other way more often. Eventually, they get so much energy that they can completely overpower the forces that were keeping them together in the liquid. They just escape. They fly right off from the surface and become a gas. Okay, I know what you might be thinking. This all sounds like a really neat theory, right? But is there any actual proof? Oh, absolutely. And the evidence comes from a really simple graph called a heating curve. It basically gives us a picture of this entire process. Check this out. This is a classic heating curve for water. So along the bottom axis, you've got time, which just means we're adding heat at a nice steady pace. And on the side, you've got the temperature. So you see, as we heat the solid ice, the temperature goes up, 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 and then something weird happens. It just goes flat. Then, once it's all liquid water, the temperature starts going up again until, yep, it goes flat again as it turns into gas. So this is the really crucial part. During the time the ice is melting and during the time the water is boiling, the temperature stays completely constant. It doesn't budge, even though we are still pumping heat in the whole time. That's just bizarre, isn't it? So that leads to the million-dollar question. If we're still adding heat, why in the world does the temperature stop rising? I mean, where is all that energy going? And here's the beautiful answer. During those flat sections, during a change of state, the heat energy we're adding isn't making the particles move any faster. Remember, that's what temperature actually measures. Instead, all of that energy is being used for one very specific job, breaking the forces that hold the particles together. It's like the energy is paying a toll, a cost to snap those bonds and allow the state to change. So you see these flat sections on the graph? They're the smoking gun. They are the hard evidence. They show us exactly where that energy is going to overcome the forces between particles. This graph is the signature that proves the kinetic particle theory isn't just some nice idea. It's a perfect description of how the world actually works. So to wrap this all up, let me leave you with one last thing to think about. We've just seen that heat is really just the energy of particles moving around. So what does that tell us about the idea of cold? Think about it. It can't be its own separate thing, can it? It must just be the absence of heat, the slowing down of that very same motion. The secret world of particles really does explain everything. Thanks so much for joining me.